for you guys to watch while I'm gone. I always put on a space video here. Okay. All right, let me put on a video. What should we put on? I'm thinking. The dream is alive? I think that all got claimed off of YouTube, dude, if I'm remembering right. Yeah, it's mostly gone. You know what? Orbital mechanics. All right, I'll be back in a little bit, guys. Enjoy this vidya. Enjoy it while it lasts. All right, I'll be back in a moment.
When ancient man looked to the heavens for guidance from the gods, he noticed star patterns and began to document their movement across the heavens. The ancients believed that the earth was flat, but around 350 BC, Aristotle proved that the earth was round. Later, about 150 AD, Ptolemy presented the geocentric theory, the belief that the earth is stationary at the center of the universe, with the sun, moon, stars, and planets revolving around it in complex orbits. In the 1500s, Nicholas Copernicus of Poland presented the heliocentric theory, the belief that the Earth revolves around the sun as it rotates on its axis. This aspect of astronomy evolved into an intricate study of planetary motion known as orbital mechanics. Today, orbital mechanics is applied to space flight and satellites that orbit the Earth or travel beyond our solar system. In the early 1600s, Johann Kepler, a German mathematician, using the data on planetary observations collected by the Danish scientist Tycho Brahe, developed 3 laws of planetary motion. Kepler's first law states,
all planets move in elliptical orbits with the Sun at one focus and the other focus empty.
applied to Earth satellites, the center of the Earth becomes one focus, with the other focus empty. For circular orbits, the 2 foci coincide. Kepler's second law, the law of areas, states,
the line joining the planet to the Sun sweeps over equal areas in equal time intervals.
When a satellite orbits, the line joining it to the Earth sweeps over equal areas in equal periods of time. If areas 1, 2, and 3 are equal, times 1, 2, and 3 are also equal. Therefore, the speed of the satellite changes depending on its distance from the center of the Earth. Speed is greatest at the point in the orbit closest to the Earth, called perigee, and is slowest at the point farthest from the Earth, called apogee. It is important to note that the orbit followed by a satellite is not dependent on its mass. A large, heavy satellite could be in the same orbit with a small, light one, each sweeping out equal areas in equal periods of time. Kepler's third law, the law of periods, relates the time required for a planet to make one complete trip around the Sun to its mean distance from the Sun.
For any planet, the square of its period of revolution is directly proportional to the cube of its mean distance from the Sun.
Applied to Earth satellites, Kepler's third law explains that the farther a satellite is from the Earth, the longer it will take to complete an orbit, the greater the distance it will travel to complete an orbit, and the slower its average speed will be. Isaac Newton, the father of classical mechanics, laid the groundwork for orbital mechanics. He combined the work of Kepler and others to formulate the law of universal gravitation and the three Newtonian laws of motion. While Kepler's laws provided a conceptual model of orbital motion, Newton's laws provided the foundation for the mathematical description of orbits. They explain why a satellite stays in orbit. Newton's law of universal gravitation.
Any two objects in the universe, such as the Earth and the Moon, attract each other with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between them.
Stated more simply, the more massive the objects are, or the closer they are, the greater the gravitational pull between them. Newton's first law of motion.
A body in motion will keep moving at the same speed and in the same direction unless acted upon by an external force.
A satellite moves in a curved path around the Earth because the Earth's gravitational pull acts as an external force on it. Newton's second law of motion.
If the sum of the forces acting on an object is not zero, the object will have an acceleration proportional to the magnitude and in the direction of the net force.
Newton's second law states that force equals mass times acceleration. It is this mathematical equation and the equation for universal gravitation that forms the basis for calculating orbits. Newton's third law of motion explains how a satellite gets into orbit.
For every action, there is an equal and opposite reaction.
If you blow up a balloon and let it go, the balloon is pushed forward by the action of the air rushing out of it. A rocket's exhaust gases are like the air rushing out of the balloon. The following illustrates how a satellite stays in orbit. If a man stands on a mountain and fires a projectile horizontally, gravity will cause the path of the projectile to curve downward and it will strike the Earth. However, if the man fires the projectile fast enough at a specific speed, the curvature of its path due to gravity will match the curvature of the Earth under it. The projectile will then fall around the Earth, becoming an Earth-orbiting satellite. A projectile fired even faster will have a flight path away from the Earth, but gravity will act to slow the projectile down, change its flight path, and pull it back toward Earth. If the projectile's velocity increased enough, a velocity sufficient to escape the Earth's gravitational pull will be reached. This velocity is known as the escape velocity. It is equal to about 7 miles per second at the Earth's surface. The preceding description did not consider atmospheric drag and the Earth's rotation, both of which will affect the trajectory of the projectile. It illustrated the principles governing a satellite's orbit. There are 6 numbers called the orbital elements, which specify the size, shape, and orientation of an orbit in space, as well as the location of the spacecraft in the orbit. Based on an orbit which is an ellipse, the 6 orbital elements are length of the semi-major axis, eccentricity, inclination, right ascension of the ascending node, argument of perigee, time of perigee passage. The major axis of an elliptical orbit is the line joining the perigee and apogee. This line is also referred to as the line of apsides. The first orbital element is the semi-major axis. It is simply 1/2 the major axis. Circular orbits have no apogee or perigee. Therefore, the semi-major axis is simply 1/2 the diameter of the orbit. The semi-major axis is used to define the size of the orbit. From this, the orbital period, or time that it takes for the satellite to complete one orbit, can be calculated. The shape of an orbit is defined by the second orbital element called eccentricity. For all ellipses, the value of eccentricity lies between 0 and 1. The larger the value, the more elliptical the orbit. A spacecraft in Earth orbit with an eccentricity equal to or greater than 1 will escape the Earth's gravitational field. When orienting an orbit in space, a 3-dimensional coordinate system must be defined. The coordinate system commonly used is the geocentric equatorial coordinate system, which has its origin at the Earth's center. This coordinate system is a non-rotating reference system in which a satellite's orbital plane tends to remain fixed relative to the stars while the Earth turns beneath it. The XY plane is the Earth's equatorial plane. The positive x-axis points to the vernal equinox. This is the point where the sun appears to cross the Earth's equator on its way north on the first day of spring each year. The z-axis is along the Earth's spin axis toward the North Pole. Nodes are points in a satellite's orbit which intersect the Earth's equatorial plane. The ascending node is the point at which the spacecraft crosses the equator going from south to north. The descending node is where the spacecraft crosses the equator going from north to south. The line joining the two nodes is called the line of nodes. The orientation of an orbit is determined by 3 orbital element angles. The right ascension of the ascending node is the angle between the x-axis and the ascending node. It is always measured eastward from the direction away from the vernal equinox in the Earth's equatorial plane. The argument of perigee is the angle between the ascending node and the point of perigee. It is measured in the orbital plane in the direction of spacecraft motion. Inclination is the angle between the equatorial plane and the orbital plane. A satellite which has an eastward velocity component at the ascending node has an orbital inclination lying between 0 and 90 degrees. Such an orbit is called a prograde orbit. A satellite which moves due north at the ascending node is in a polar orbit. Polar orbits have an orbital inclination of exactly 90 degrees. A satellite with a westward velocity component at the ascending node is in a retrograde orbit and has an orbital inclination between 90 and 180 degrees. The 5 orbital elements explained thus far describe the size, shape, and orientation of the orbit in space. The final element is a time value used to locate the satellite in its orbit. A satellite moves in a very predictable manner. It stays on schedule. Thus, if the time at which a satellite passes a particular point is known, the time when it will pass any other point can be determined. The particular point chosen is perigee, and the time of perigee passage is the last of the 6 orbital elements. The 6 orbital elements depict a spacecraft's orbit in non-rotating coordinates. To visualize an orbit relative to the rotating Earth, a projection traces the spacecraft's position on the Earth's surface. The projected path is called the ground track. As a satellite orbits the Earth, the ground track shifts westward. There are 2 causes for this. First, the primary contributor is the Earth's rotation toward the east under the orbital plane. Second, because the Earth is not a uniform sphere and bulges at the equator, its gravity is greatest at the equator. This causes the orbital plane to rotate slowly around the Earth's polar axis in a motion called precession. Precession is toward the west for prograde orbits and toward the east for retrograde orbits. For low Earth orbits such as those of the Space Shuttle at 150 miles altitude, the westward shift of the ground track due to the Earth's rotation is about 22.5 degrees, while the shift due to precession is only about a half degree. The inclination of a satellite orbit determines the north and south latitude limits of its ground track. The minimum orbital inclination is equal to the latitude of the launch site and is achieved by launching due east. For example, if a satellite is launched due east out of the Kennedy Space Center, which is located at 28.5 degrees north latitude, its orbital inclination will be 28.5 degrees, and the limits of its ground track will vary between 28.5 degrees north latitude and 28.5 degrees south latitude. If launch azimuth or direction of flight at launch measured eastward from due north is increased from due east, the orbital inclination angle increases as well as the maximum latitude of the north-south ground track. Therefore, the latitude limits of the ground track equal the new launch inclination. Similarly, if launch azimuth is decreased from due east, orbital inclination once again increases as well as the latitude limits of the ground track. The maximum practical inclination from a Kennedy Space Center launch is 57 degrees. This limit is imposed for safety considerations in order to keep the spacecraft and its booster system from flying over land masses during the ascent phase. To obtain an orbit with an inclination greater than 57 degrees, the spacecraft is launched from Vandenberg Air Force Base in California. Vandenberg offers the opportunity for southerly launches with orbit inclinations between approximately 70 degrees prograde through 138 degrees retrograde. A significant advantage of launching from Vandenberg is the capability to economically achieve polar orbits with ground tracks covering all latitudes, from the North Pole to the South Pole. The Earth is constantly turning, and all points on its surface have an eastward velocity, with the greatest velocity occurring at the equator. The farther the launch site is from the equator, or as launch azimuth is increased or decreased from due east, less of the Earth's rotational velocity will be imparted to the launch vehicle. This requires more fuel to get into orbit, or payload weight will have to be decreased. Launches due east from a position on or near the equator, such as the Kourou launch site in French Guiana, used by the European Space Agency, acquire the advantage of a free velocity gain of about 1,500 feet per second. This compares to the approximate 1,300 feet per second gain available at the further north latitude of the Kennedy Space Center. Launching from an equatorial site offers a significant advantage in payload weight capability and minimizes the amount of fuel needed to achieve an equatorial orbit. Since many satellites operate in equatorial orbits, these are important considerations. Spacecraft are launched within a specified time interval called the launch window. Some of the factors affecting the launch window are launch and orbit lighting conditions, sun angles, payload orbit requirements, rendezvous phasing if a rendezvous is planned, tracking and communication requirements, and collision avoidance with other orbiting objects, to name a few. One of the factors defining the launch window for the Space Shuttle is launch lighting conditions, which can be illustrated by plotting time versus day of year. On this plot, we see daylight and darkness at the launch site. The longer daylight hours occur in the middle of the year, summertime. If daylight conditions are required for a convenient emergency landing site for the Space Shuttle, the launch window would now look like this. During the winter months, the available launch window for lighting conditions alone can be as little as 3 hours per day. When combined with the many other launch factors, the launch window becomes even more constrained. The choice of a particular launch vehicle for a mission depends upon the weight and size of the payload and the desired orbit. Expendable rockets used to place spacecraft in orbit usually consist of several stages that may incorporate both solid and liquid propellants for propulsion. When the fuel in each stage is depleted, the spent stage is jettisoned. Staging offers the advantage of discarding weight when it is no longer needed. The Space Shuttle is a two-stage system. At liftoff, the 2 solid rocket boosters and 3 Space Shuttle main engines are all producing thrust. After approximately 2 minutes of flight, at an altitude of 25 miles, the fuel in the solid rocket boosters is depleted and they are jettisoned. The 3 main engines, fueled by liquid oxygen and liquid hydrogen carried in the external tank, continue to burn for several minutes until the shuttle reaches its cutoff velocity. At this time, the main engines are shut down and the external tank is jettisoned. 2 additional burns using the orbiter's maneuvering system referred to as ohms are required to place the orbiter in its final orbit. The ohms 1 burn occurs about 2 minutes after main engine shutdown and establishes the orbital apogee point. The ohms 2 burn takes place approximately 30 minutes later and circularizes the orbit. Once satellites are launched and put into orbit, it is often necessary to change the orbit with an on-orbit burn. The common term used in describing on-orbit burns or engine firings is delta V. Delta V is the incremental change in spacecraft velocity measured in feet per second resulting from the burn. The amount of fuel used during a burn depends on the desired delta V change and the mass of the spacecraft. Because the amount of fuel carried is limited, fuel consumption is one of the primary considerations in spacecraft mission planning and is critical to orbit lifetime. On orbit, a spacecraft can thrust in any direction. burns along the flight path, forward and backward, are the most common. A unique feature of any orbital burn is that if no other burns occur, the spacecraft will later always pass again through the point of burn. Forward burns increase the spacecraft's velocity and are known as posigrade burns. With posigrade burns, the flight path of the vehicle will be raised at all points except the burn point. Burns opposite the direction of flight, which slow the spacecraft down, are called retrograde burns. For retrograde burns, the orbit will be lowered at all points except the burn point. The greater the delta V, the greater the difference between the pre-burn and post-burn orbits. Burns can be combined into maneuver sequences to change orbit size, shape, or orientation. One of the most common maneuver sequences is made up of two burns and is used to accomplish an orbit transfer between two circular orbits in the same orbital plane. The most energy-efficient transfer between two orbits of this type is the Hohmann transfer. The Hohmann transfer is actually 1/2 of an elliptical orbit with its perigee in one of the orbits and its apogee in the other. The burns occur at the perigee and apogee of the transfer orbit. The use of the Hohmann transfer minimizes the delta V required, thus having the advantage of using minimum fuel. The disadvantage of the Hohmann transfer is that it takes longer than most other transfers. The type of the transfer sequence depends on the mission and the amount of fuel available. For example, a space rescue where time is critical might use a fast transfer, while a routine satellite deployment where fuel saved for later use is important would most likely use a Hohmann transfer. The burns discussed so far have all been maneuvers in the original orbital plane and do not affect orbit inclination or node position. There are situations which require an orbital plane change, such as setting up a rendezvous or placing a satellite in an equatorial orbit. To change the inclination, the thrust vector must be directed at an angle to the orbital plane. A thrust with a component that is perpendicular to the orbital plane at either the ascending or descending node will rotate the orbital plane about the line of nodes. A northerly out-of-plane thrust at the ascending node will increase the inclination of a prograde orbit, while a southerly thrust will decrease it. Out-of-plane thrusts require considerable amounts of fuel and are performed only when absolutely required. The Space Shuttle, for example, using all of its onboard propellant, is capable of an on-orbit plane change of less than 3 degrees. Satellite orbital planes and altitudes are determined by their design mission, which very often includes a field of view requirement for optical or communications purposes. The field of view of a satellite is defined as the area of the Earth's surface that is in view from the satellite at any given time. Satellites in high orbits have greater fields of view than those in lower orbits. For example, a satellite at an altitude of 800 nautical miles has a circular field of view with a diameter of about 4,100 nautical miles. A satellite at 200 nautical miles has a circular field of view with a diameter of about 2,000 nautical miles. Low-orbit satellites are often used for photography and other types of Earth observation. A satellite placed in a low-inclination circular orbit at an altitude of about 19,300 nautical miles will have an angular velocity exactly equal to that of the Earth's. The satellite would seem to remain stationary in longitude as viewed from the ground. Such orbits are called geosynchronous and are used to provide a continuous communications capability among any system of ground stations within their field of view. The geosynchronous orbit field of view is constant and is limited to a latitude zone of about 70 degrees north and south of the equator. Effective satellite communications from geosynchronous orbit is not possible at either pole. However, because of their altitude, their field of view covers nearly half the globe. A special type of geosynchronous orbit with an inclination of 0 degrees is called a geostationary orbit. It appears to hover over a fixed point on the Earth's surface at the equator. Most U.S. communication satellites are in geosynchronous orbits, providing near worldwide communications coverage. For effective communications at high latitudes, the Molniya orbit is used. Molniya is the Russian word for lightning and is an orbit used extensively by the Soviet Union for its communication satellites. The Molniya orbit is highly eccentric with an apogee that is near the geosynchronous altitude and an inclination of about 63 degrees. The satellite slows down at apogee in the northern hemisphere and whips through perigee in the southern hemisphere. This provides communications in the northern hemisphere for up to 75% of its orbital period. Several satellites properly spaced in Molniya orbits can provide constant communications at the northern latitudes. Navigation satellites, such as the U.S. Navy's Transit System and the Joint Service Navstar GPS Global Positioning System, use lower orbits so that a user can receive signals from more than one satellite at any time. Another frequently used orbit is known as a sun-synchronous orbit. These take advantage of the precession of the orbital plane caused by the Earth not being a perfect sphere. All sun-synchronous orbits are highly inclined retrograde orbits which precess eastward around the Earth's polar axis at the rate of 1 revolution per year. Since the Earth-Sun line also revolves eastward at the rate of 1 revolution per year, the orbital plane will maintain a constant orientation relative to the Earth-Sun line. If the satellite's period is then synchronized with the rotation of the Earth, it will pass over the same point on the Earth's surface at the same local time at a regular interval. A sun-synchronous satellite ensures that a constant sun angle and uniform lighting exist for the same field of view from pass to pass. Satellites such as those in the Defense Meteorological Satellite Program and Landsat are sun-synchronous, imaging the entire Earth on a regular schedule. The gravitational attraction of the Earth on a spacecraft causes it to move in its orbit around the Earth. There are other, much smaller forces which will cause a spacecraft to deviate from its desired orbit. These forces cause what are known as orbital perturbations. Orbital precession, which is used to obtain sun-synchronous orbits, results from the perturbing effects of the Earth's non-spherical shape. Other perturbing forces are the gravitational pull of the Sun, the Moon, and planets, and solar winds, which are charged streams of protons and electrons that heat the Earth's atmosphere and increase atmospheric drag. In most cases, perturbing forces can be compensated for in the spacecraft and orbit design and present no major problems. If the forces disturb the orbit too much, thrusters can be fired to re-establish its desired orbital orientation or altitude. This is particularly true for spacecraft orbiting at very low altitudes, where the effects of atmospheric drag are greater and, if not compensated for, will eventually cause the spacecraft to deorbit. A spacecraft's operational lifetime is frequently limited only by the amount of fuel available to maintain its desired orbit. When its useful life is complete, a satellite is left in orbit or is deorbited, burning up when re-entering the Earth's atmosphere. When the Space Shuttle completes its orbital mission, it executes a precise retrograde burn to initiate its controlled return to Earth. This burn occurs nearly halfway around the Earth from the landing site. The new orbit established by the retrograde burn causes the orbiter to enter the Earth's atmosphere about 4,000 miles from the landing site. During the period the orbiter descends from its orbital altitude to atmospheric re-entry, its attitude is maintained by the use of reaction control jets located in the nose and tail of the orbiter. Once the orbiter enters the Earth's atmosphere, its wing and tail aerosurfaces begin to become effective and gradually replace the jets for attitude control. As the orbiter nears the landing field, it maneuvers to a long, straight-in approach at an angle of 17 to 19 degrees. Nearing the runway, it executes a flare maneuver to reduce its sink rate and glides to a touchdown at approximately 230 miles per hour. As the orbiter rolls to a stop, our journey into the world of orbital mechanics comes to an end for now. This is only the basics of orbital mechanics, an intricate study of planetary and satellite motion. The next time you see a launch, you will see it from a different, somewhat knowledgeable perspective. You will understand the fundamentals of spaceflight.
You know, the projector. Any questions? Quite's like, nope, I don't think I will. No, I don't think I will. But I'll pretend. Yeah, just rocket go brrr. That's all you gotta know. SpaceX audio is online. Thank you. Dank. That's how you say that, right? Dank. 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 Way too dank. All right, guys. So we're gonna do a quick space news here, but the reason why I switched over from KSP is because we got a Falcon 9 launch happening, and let's see, this will happen about 45 minutes from now. Let me get the mission control audio up. Deck. Who is Deck? Why are you Deck? Who is Deck? Mission control audio. There we go. I'll get the mission control audio up. All right. So here. Let's see what we got. Let's see. We kind of went over the booster getting moved today. Booster 7 was taken off of the pad. Now here, I'll tune you over to Starbase Live here. Booster 7 was taken off the pad. It was pretty rad. Let's go back over here somewhere. Isn't a CR-25 encounter a bit much even for chat? Who? There we go. The 7 was the one that had a little bit of a fart yesterday. Ooh, what happened over there? Ooh, that's okay. What time is the launch? Launch is in about 50 minutes. 50. So I figure we'll go over the Starship footage for the day and anything else. We were supposed to get more James Webb pictures today, but I haven't seen it being incessantly linked in chat, so not 100% sure what's going on there. I'm not going to lie to you. Doesn't hurt being Ricky Bobby. I'm not going to lie to you. So we'll try to get through the rest of this stuff here. We tried to. Oh, okay. I was busy, man. All right, here's the new picture from Webb. It is a picture of Jupiter. Ready for... Hey, NASA Solar System, are you ready for your close-up? As part of Webb's prep for space, or Webb's prep for science, sorry, old habits. We test how the telescope tracks solar system objects like Jupiter. Webb worked better than expected and eventually caught Jupiter's moon, Europa. That's nice. Cool. Let's go see what we got here. Oh, wow. Cool. I like it, but it looks like it's from 1972. I think this thing might be a little bit close. A little bit too close for web. That's actually pretty damn crisp. Like I said, Pop, I don't know too much about this, but I'm pretty sure Jupiter's awfully close for web. It's really, really freaking close. So, like, think about you have a camera, right? You have a camera and you're taking a picture or something, right? And then you put your hand in front of it, your hand's going to be all blurry. It's not going to be very good quality because it's not in the right focus. I think that's what's going on, but I'm pretty sure they could focus it as well. This might just be a non-color corrected picture. Definitely a thermal image. Yeah. This is also, that's also infrared, which is pretty, if that's infrared, damn, that's pretty good. That's pretty damn good for IR. Yeah, that's pretty freaking good. Yeah, exactly, Harass. Yeah, you got it. I think that's how that works, but I could be wrong. This is a quick and dirty picture. Yeah, I agree. Overexposure, I think Jupiter puts out a lot of light. Yep. Definitely. So there's the new pictures from James Webb. Once again, anytime there's a new picture popping out, I will link it here for a space news. The next thing is that NASA SLS, the NASA SLS Twitter account. The NASA SLS Twitter account tweeted this today. I was about to say tweetered. Yep, okay. Good. Save the date. So NASA Northrop Grumman will perform a full-scale static test of an SLS solid rocket booster motor on July 21st to support the future Artemis missions. The test will air live on our Facebook page and the NASA Marshall YouTube. Okay. So it looks like they're going to do another 5-segment booster test here, which is pretty good. That's pretty sweet. And then, you think you know how big this booster is, and then you look at the two dudes that are standing there and go, oh. Yeah, that's not small. And the answer is no. No, it's not. What you're seeing there is the single most powerful solid rocket booster and one of the most powerful single rocket boosters, or singular rocket engine ever designed. That thing makes 14,000 kilonewtons of thrust. It's, what is that roughly equivalent to? About 2 Saturn V engines. So about 3 million pounds of thrust? Somewhere around there. Yeah, 5-segment SRB for SLS. How much power does it make? It makes 1 power. Yeah, that's a lot of oomph behind it. That's a lot of oomph. Should be the first stage for Ares 1. Yeah, there, I said it. There, I said it. Big whoop. Want to fight about it? So, yeah, we should see this thing literally rip off the side of a mountain, because if you go and look at where... So, that's Northrop Grumman's test stand in Ogden, Utah. It's out in the middle of nowhere. But if we go out here, we pop out here, take a look-see. Ogden's up here, north of the Salt Lake. The Great Salt Lake. Where are you? There's Promontory Point, which is pretty sweet. Where are you? I always find it, and then I always lose it. I think it's over here somewhere. No. Whatever's left of the Salt Lake. Yeah, something like that. Alright, hold on. We'll do it this way. Lake Mead is almost gone too. Yeah. It's a drought combined with overuse of water, from what I understand. Not good, bros. Not good at all. I'm trying to find the SRB test stand. Sometimes I can find it like instantly. Ah, there it is. Sometimes I can find it instantly. Other times I can't. Here they are. So, where's the 5-segment SRB test stand? Oh yeah, here we go. Here they are. It's the one that basically scraped all the topsoil off of the mountain right here. Yeah, if you look, see that? Yeah, that's the SRB test stand. Yeah, there's 2 of them. There's another one over here. These are the ones that these are there for testing. They were testing 4-segment boosters for the shuttle program, and now they're testing 5-segment boosters for SLS, which is pretty cool. Fueling pole is coming up in a few. Good. Yeah, look, you can see it literally scraped off all the topsoil down to bedrock. You can see the sedimentary bedrock under there, which is, yeah, rockets. Mining application. Pretty cool, huh? This is where Northrop Grumman does a lot of SRB testing. They have all kinds of SRB test stands. Now I know what people are going to ask. What are the other SRB test stands? Missile first stages. Yeah, missile stages. Anytime you see a big scuff mark in the ground, that's where they've been testing SRBs. Rockets as a strip mining tool? Dude, I can't decide whether that would be a really good idea or a really bad idea. On one hand, that seems like it would be a really awesome idea. But on the other hand, I can't help but think that someone would get hurt. But then again, that kind of happens with mining. Whoa, CRS-25 has stuff in the trunk. Yeah? Yes. So, interesting thing, if you follow the road, the heavy industrial road, you know I love doing this. Hey, look. Weird road radius. Alright, let's go. Look, another one. Another weird road radius. It's also concrete. Interesting. And, oh look, we have a weird, there's another one of those stupid roads with the bike lanes on the side. Because, you know, someone's going to ride their bike all the way over here, right? Yeah, sure. In the States? Yeah, I'll believe that when I see it. Okay. So, hint.
Launch director on countdown 1.
Oh.
We are go for propellant loading and launch.
Okay. That was the launch loop right there. Is that where they test the salami lid? No, that's where they test your mom. Got him. Alright, so check this out. Look, weird radius road again. Oh, they're loading heavy stuff into those bunkers, whatever they are. Let's follow this road. Right? Once again, you can tell that this road is designed for heavy equipment because it has these weird shoulders on it. That's always a dead giveaway. And if we follow this road all the way this way, across that, we keep going. Where are we? Keep going. Okay, now we're getting into civilization here. All right. Right here. Let's take a look. Here we go. Alright, look at this intersection. That's a very weird looking intersection, right? You got a 4-lane road over here, and then the radius on this turn right here is way bigger than the radius on that turn. Hint, hint. Let's go down here and take a look. Where does this road go? Let's look for another weird radius. Spoiler alert, it's right there. See? And then they turn it in here. This is where they load up the SRB train. So the SRB segments are made at the factory down the road that we went to, and then they're loaded up on a train right here. And you can see the SRB train is right there. You just got to follow the heavy infrastructure. And then that train takes the boosters and the booster segments all the way down here, where the booster drop-off point is, or the SRB segment drop-off point is, which is right there. Do not hump. See, there's another one of those SRB train cars right there. Do not hump. What is that, Thomas? Why not just use them there, save on petrol?
This is the launch director on countdown
LD?
with abort instructions. For non-urgent no-go conditions, freeze the CE or LD, and they will approve aborting the countdown. For urgent issues affecting the safety of the operation, operators shall call hold on the countdown name and state reason for hold.
Yeah.
Launch control will abort the launch auto sequence immediately and proceed into the launch abort auto sequence. At T-minus 10 seconds, launch control.
Hey, Barry.
will
What's
off
going on, bro?
and finally automated abort abort criteria.
Been trying to catch one of your streams for weeks. Yeah. So that was the auto abort criteria for launching Falcon 9. They basically said if anybody sees anything, yell hold, and we'll stop the count immediately. That's they do that every time. Yeah, Thomas, I'm kind of wondering where that came from. Yeah, Devlin, you saw it too. That's not an external thing, to say the least. Okay, launch auto sequences started from the mission control loop here. So, in about 35 minutes, we should see a Falcon 9 launch. The coverage should be picking up soon. NASA is broadcasting that?
Discovery, go and throttle up.
Oh, yeah? Yeah, that's, 23 Skidoo! Would you stop calling me Phil? Which NASA channel is broadcasting that, Plutonium? Or not Plutonium. Plutonium at the reset. Thomas... Yeah, okay. That... Okay. They're showing that. Yep, they took it off. They switched to weather reports. What's the problem? No, nothing. Nothing. See you tomorrow in class, Miss Vaughn. Yeah. Yeah, well, it seems like someone just decided to stream that without really, Yeah. You'll blow it! Do you have any screenshots of Collins in the SPH? Trying to get the aerodynamics right, but she keeps spinning out on the glide. 9 years of KSP and 2-year break has me scratching your head. Spinning out. What are you doing when it's spinning out? For totally non-blessed rocket reasons, how much of rated thrust did the RS-25 get to? 109%. Well, it will get to 109%. I think during the shuttle era, it only got to 107, but I'm not sure. Dang it, Bobby. Dang it, Bobby. Do I look like I know what a JPEG is? I just want a picture of a goddamn hot dog. Yeah, Devlin here. Look at this thing. Huh.
Discovery, go and throttle up.
Oh. Well.
The launch director on countdown. Prop load has started.
Prop load has started.
Count auto has also started.
Barry, you got to tell me what's going on. Anesthesis, did you have Collins down to where you could pull off any roll program you wanted? Yes, it could fly pretty much anywhere. Yep, weather seems to be holding just fine. This mission is going this way. That way. Anvil threat sector. Yep. Looks like got some scattered showers throughout Orlando there. Up just northeast of Sanford, you got some looks like lightning. Intra-crowd light. Dude, this is excellent. Who is streaming this? Normally correcting on a simple glide slope to land on a runway, Enterprise style, but she's spinning out when I bank or turn. Barry, go into the SPH, look at your center of mass, center of lift, take the shuttle, and then tilt it upright, and then tilt it to the right. Like, do this, and then pitch up, and then do that, and watch what your center of lift is doing. Yeah, there's something somewhere that it doesn't like. 18 knots, steady, stable. Bonus points if you know what PSFB is. I'll try it when I'm on KSP next, sure. Yeah, you could basically do wind tunnel testing. Primitive wind tunnel testing, but wind tunnel testing nonetheless. I have terrible hat hair, so we're putting the hat back on. Yeah, Thomas, of course. Portland Space Force, Patrick Space Force Base. Alex, it's the Air Force base that's near. So we got a lot of lightning just north of Orlando. Intra-crowd lightning. No heat lightning out on the Cape tonight. Yeah, I'm not entirely sure that this should be a stream, but this is great. This is really good stuff. There was the weather. That was the weather data from all the different pads. The range has a stick version of the standard Windows 10 background where they embed the range logo in it. That's kind of cool. Okay, no lightning watch there anywhere near the Cape. We should be good for a launch. You know what? We're already there. I'll just switch us over to launch coverage. Boop.
Discovery, go at throttle up.
Hey, Stormy, 22-month resub. Thank you. Yeah, I got a little bit of cloudage happening there. SpaceX is live with pad views. Well, oh, it's the same thing. Nice.
Discovery,
Where are you watching the weather info? Places. I love that they have an unactivated copy of Windows. Do I look like I know what a hot dog is? Okay. Ooh, Dagron. With a crane in the background. Gee, I wonder what that crane's building. Dagron, the Burninator. Do I look like I know what an activated Windows is? Yeah, it looks okay. Yeah, we should be good to launch. There's a lot of clouds over Central Florida right now, but everything should be good. Cape looks okay. Oh yeah, Thomas? The crane is there to destack Dragon due to another Hypergol leak? Oh yeah, I'm sure that's the reason. There's all the wind sensors around the Cape right there. I know guys that worked on that. How many people on the capsule? This is an uncrewed resupply mission, Sun Temple. We got winds 18 knots going west to east, southwest to northeast. Observed 18 knot steady state winds. No lightning watches in the area. Okay, activate Windows. There's the radar. Oh, it's clear for me. It's clear up by me. You see that? Is it? Oh, yeah, I got a little thunderstorm. A little thunderstorm there, but nice and clear up in Boston. That's good. The computer also says it's 12:18 a.m. 12:19 a.m. Oh, it's that computer's on. This computer's on GMT. Is this another telescope? No, this is an uncrewed resupply mission. Hi, Nick. There's local windage. Yeah, it's a little more windy down at the Space Force Station than it is up at KSC. Google Maps just updated the sat image for Boca Chica. Cool. Area divergence. Wow, this is good stuff here. It was field electric sensors, Devlin? Oh, even better.
Is in countdown. Falcon 9 is in startup.
All right.
Dragon, SpaceX, go for launch.
Here we go.
We're about 24 minutes and counting from liftoff of this Falcon 9 rocket for NASA's and SpaceX's 25th commercial resupply services mission. The Dragon spacecraft you see there will fly more than 5,800 pounds of science, supplies, and food for the astronauts aboard
2,600
the
kilograms.
Space Station. Good evening, and thank you for joining me for live launch coverage of CRS-25. I'm Megan Cruz. You just saw Falcon 9 and Dragon on Launch Complex 39A here right behind me at Kennedy Space Center. Fueling began about 10 minutes ago, and we have an instantaneous opportunity to launch at 8:44 p.m. Eastern Time. These resupply missions are important so NASA
hot.
and its international partners can continue to conduct microgravity research aboard the space
Jackets
station.
are pretty hot.
Over the last 21 years, thousands of experiments have led to scientific advancements right here on Earth. Today, more than 24 experiments, including some that will study Earth's climate, are packed away in Dragon awaiting launch. Let's go now to SpaceX headquarters in Hawthorne, California, where we have Shiva Bharadwaj to tell us more about this mission, which NASA and SpaceX were initially targeting last month for launch.
Thanks, Megan. It's great to be covering today's mission in partnership with NASA. And like you just said, we spent the last few weeks working through an issue on Dragon after teams discovered a small vapor leak. Since then, we've completed thorough inspections and replaced the components that could have been degraded by exposure to this vapor. And we've been working hand in hand with NASA throughout the process. And now we're ready to launch. This year also is the 10-year anniversary of Dragon becoming the first private spacecraft in history to visit the International Space Station, deliver cargo, and then return to Earth. 5 years ago was our first reflight of a Dragon on the CRS-11 mission, and since then we've made 31 flights to the space station with 14 reflights of Dragon. Today's mission adds to that tally and will mark SpaceX's 30th launch of 2022. It'll also mark our third Dragon flight this year, following the crewed launches of Axiom 1 and Crew 4 back in April. Now on screen is our Falcon 9 rocket and the Dragon spacecraft sitting at the very top. The capsule flying today is our first third flight of a new cargo Dragon, which previously
that's the only place they have space for it, John.
the CRS-21 and 23 missions last year.
Sorry,
now, this version of Dragon is certified for up to 5 flights, and it'll be joining the Crew 4 spacecraft, which is currently docked at the station. Moving down is our Falcon 9, our reusable 2-stage rocket. It's actually 2 rockets in one. That lower part is called the first stage, the upper the second stage. Today's Falcon 9 will be flying for its 5th time, and as that name suggests, Falcon 9 has 9 Merlin 1D engines at the bottom of the first stage. They are what accelerate the vehicle through the Earth's atmosphere and to those various orbits in space, and we've got a great photo of those 9 engines before we roll them out to the pad on Tuesday morning. We're going to be attempting to recover this first stage on our drone ship named A Shortfall of Gravitas, which is off the coast of Florida out in the Atlantic Ocean. Now, above the black inner stage of our first stage is the second stage. The stages separate about 2.5 minutes into the flight.
Shot looking at the bottom of the
engine.
engines.
Ignites its Merlin vacuum engine to carry Dragon to the targeted orbit. A little later on in the show, we're going to talk about how Dragon navigates to the station after we separate from Falcon. But for now, I'm going to turn it back over to you, Megan.
Sounds good, Shiva. Thank you. In addition to SpaceX, NASA teams both here in Florida and Houston are monitoring today's launch. You'll hear from Sandra Jones, who you see in there inside with Mission Control in Houston. But first, let's check in with Daryl Nail, who's monitoring the launch team here at Kennedy. Daryl.
Yeah, thanks, Megan. Everything looking good so far here from Hangar AE at the Space Force side of things. You can see behind me the data and telemetry flow through this building. We're happy to be here and appreciate them having us here. Out to the rocket we go. And you can see it is twilight here on the eastern coast of Florida at historic Launch Complex 39A. You can see the rocket is being
it should
tanked.
be
The
chill
launch
down.
director gave the go around 8:06 p.m. for tanking to begin.
So what they're doing here, they've already started tanking the first stage. The first stage is filled up via umbilicals that are, or via what's called a tail service mast that's down at the bottom down here. There's 2 tail service masts on either side of Falcon. One is kind of behind the camera and one is right there. You can kind of see it. It's down by where the 5 is in CRS-25. First stage prop load began a little while ago. And what that big vent out the side, like up the white transporter erector on the side there, what that is basically they're purging down the fuel lines and chilling down the fuel lines that go to the second stage. SpaceX tries to time this so the first and second stage, well, not tries, they do time it. So the first and second stage end up getting filled up with liquid oxygen at the exact same time. That way you maximize the performance of the rocket because it has the fullest tank of gas right when you go to launch. Tank of gas, it's liquid oxygen. That's the real kind of Achilles heel here. Now, what does that mean? So what do you mean? What is it? What? If they fill it up, what do you mean? The fuel's going to go somewhere? Yes, it will. The liquid oxygen that's inside boils off. It's really, really freaking cold. Oxygen, that was mostly nitrogen that you're breathing. Oxygen likes to exist as a gas down here, so keeping it as a liquid makes it at high pressure makes it boil. So they try to time it so they have the maximum amount of propellants before they get a boil off. So that's what that TE chill down on the side and that big vent was. They're basically filling up the fuel lines up the side of the transporter erector for the second stage to time it so the second stage and the first stage fill up with liquid oxygen at the exact same time.
And when Dragon arrives to the International Space Station on Saturday,
this will go north,
I
think, John.
Forward port of the Harmony module. NASA astronauts Bob Hines and Jessica Watkins will be on tap to monitor that approach.
Oh, ISS shot.
Dragon is slated to spend about 1 month attached to
Nice.
the International
That's the Crew
Space
4
Station
Dragon right there.
before it returns to Earth with research and return cargo and splashes down off the coast of Florida. For now, everything continuing to look good on the station side for today's launch, so back over to you, Megan.
Thinking about Sandra and before that, Daryl. We are now
We'll
about
check it in a
17
little bit,
minutes
Rogue.
and counting from liftoff of CRS-25. Let's check out some of the science flying on this mission.
Yes, let's. Peppers! Let's take a look at what's on board.
Discovery, go at throttle.
The Earth's surface mineral dust source investigation. EMIT will assess the heating and cooling effects of mineral dust in Earth's atmosphere and measure mineral composition of it when off the page. Biopolymer for in situ capabilities. Students will test a novel process for building structures in space, on Earth, using local resources. Dynamos. Researchers will compare the interaction of a group of soil microorganisms on station and on Earth. Findings could influence the design of future life support systems. Oh, beaver cube, eh? Oh, yeah, that's good. Oh, this CubeSat will use cameras to Take color images of Earth's oceans and detect the temperature of cloud tops and ocean surfaces. Oh, BeaverSat. Immunoscience. Scientists will study immune cells in microgravity to uncover a new method to treat immune system aging and protect astronauts. Genes in Space 9. A student DNA experiment will seek to validate the use of biosensors as a simple tool for medical diagnostics and environmental monitoring. These experiments will join hundreds of ongoing investigations aboard the orbiting laboratory. Follow at ISS Research to learn more. Would you like to know more? Whoosh! I'm doing my part. Whoosh!
A lot of impactful research going on.
Back to you, Megan.
Launch, and let's take a closer look at some of those that you saw in that video, starting first with EMIT, which stands for Earth Surface Mineral Dust Source Investigation. Joining me now is EMIT's principal investigator, Rob Green, and we also have NASA's senior climate advisor, Dr. Kate Calvin. Great to have you here.
Wonderful to be here.
Perfect. So let's take a look at some video of EMIT, Rob. So EMIT is going to be attached to the outside of the space station, and it's going to study mineral dust. But what is mineral dust?
So mineral dust are the tiny particles of rocks in the dry land regions of our planet that, under conditions of high winds, are launched into the atmosphere. In the atmosphere, because they can be different compositions, they can heat or cool our planet, play a role in cloud formation, and many other impacts.
Is that the Salton Sea?
Right now, we know about mineral dust by about 5,000 different measurements that have been analyzed around the Earth. When EMIT is done, we will have 1 billion direct observations of the minerals in these dry land regions to advance the science of how mineral dust can heat or cool our planet.
And I think it's important to understand for people that, you know, we're not just focused on these arid regions. When you have dust storms, you can see a dust storm in Africa end up affecting us in Texas, per se. So why is it important to study these dust storms, and in particular to understand how they might heat or cool the Earth?
Well, as you point out, it's a global phenomenon on every continent except perhaps Antarctica, and that dust can travel thousands of miles from Africa to Florida to Texas, and it has impacts throughout the Earth system there. And then heating or cooling, when you have a global phenomena, you've got to take it into account. Are those dust particles absorbing energy, heating our planet, or are they scattering light back into space and cooling our planet? So we need this information so the Earth system models become more accurate, so we understand what's happening now and in the future, and those are the two primary objectives of EMIT.
Yeah.
Doctor,
so
when will then be now?
EMIT is going to be a real tool for us when we're studying climate change and just the Earth's climate, and it's no surprise that EMIT is one of a fleet of Earth-observing spacecraft.
Yeah, one of NASA's most important missions is our home planet. We have more than 24 satellites and instruments in orbit, including several on the International Space Station, that observe the Earth. So we can see things like carbon dioxide, vegetation, changes in the mass of ice sheets, and much more. And once EMIT is put onto the International Space Station, it'll join that fleet.
Coming out the bottom.
Wow. And I do know that it's not just what we have orbiting the Earth. There's also a lot of research
being done on
the ground.
The last Delta II payload.
The whole portfolio of climate research that we're doing. How will this help us address climate change?
Well, the more we know about the planet, the more we can use that to provide to local decision makers, stakeholders, and the public about what's happening on Earth.
Swomey?
Awesome. Guys, thank you so much. I appreciate your time.
Thank you.
And EMIT isn't the only experiment inside Dragon that will study Earth's climate. Students from MIT built what you're about to see on the screen here. This is called Beaver Cube, and it's named after the school's mascot, Tim the Beaver. It's a small satellite about the size of a shoebox, and once deployed, it will measure cloud properties, ocean surface temperatures, and ocean color to analyze Earth's climate and weather systems. T-minus about 11 minutes and counting from liftoff of NASA's and SpaceX's 25th commercial resupply services mission to the International Space Station. Let's bring back Shiva now to tell us more about Dragon.
I'm a little disappointed that it doesn't measure beaver dams.
Now, Dragon is capable of transporting people as well as environmentally sensitive cargo to and from Earth orbit, like we are on today's mission. Starting from the top of the nose cone to the bottom of the trunk, it stands about 27 feet tall and is made up of two main sections. The pressurized capsule and the trunk, which is used for unpressurized cargo and supports the spacecraft on ascent and during on-orbit operations. Now, after separating from Falcon 9, Dragon will autonomously make its way to the International Space Station using its navigation sensors and its engines. The capsule has 16 Draco engines, which are used to get the spacecraft from one place to the next. Now we've got 12 of those service section Dracos near the bottom of the capsule and 4 near the top of the forward bulkhead underneath the nose cone. Those forward bulkhead Dracos are primarily used for high-thrust maneuvers like the orbit changes that we'll need to get to station and eventually, in about a month, to get back home to Earth. Each of those thrusters are capable of generating about 90 pounds of force in the vacuum of space. The service section Dracos are used primarily for pointing and for operations in proximity to the space station. You can actually see them firing here in these clips taken from the International Space Station on various different Dragon missions as they were approaching the orbiting laboratory. And just like those Merlin engines on Falcon, we also reuse the Dragon thrusters, the Draco thrusters, once that spacecraft returns to Earth. Dragon and Falcon continue to remain in good health, and we're ready to support the on-time liftoff around 8:44 p.m. With that, back to you, Megan.
Perfect news, Shivan. That's what we like to hear. And 2 people very excited about today's launch are right here next to me. We have Claire Green and Benjamin Whitfield, both of Arkansas State University. They actually have an experiment on board and are about to tell us about it. Great to have you here.
Nice to be here.
All right, I know you're so excited. I love it. So let's take a look at the screen. We have some pictures of when the team was here earlier, a couple of weeks ago, and you guys were prepping your experiment. What are you guys studying?
So we are studying waxworm larvae and their unique ability to break down thin plastics, thin plastic bags, into a non-pollutive byproduct. And we're very curious to see if they could still do this process in microgravity or aboard the space station.
Yeah, so we know that this happens on Earth. Why do you want to see if this happens in microgravity?
Well, that's pretty neat.
Well, the application of breaking down plastics is beneficial anywhere. It's a problem that we're learning how to deal with. So if we can learn how to deal with it on Earth and in the space station, then we can extrapolate that to other environments.
Why are you guys interested to see how this will react in space? Is it because we as an organization, NASA, we are thinking about going farther than we've ever been before?
That's exactly what it is we are proposing this as a long-term space travel waste management system because plastic is lightweight, it's cost-effective, it's not going anywhere, and we don't want a pollution problem like we've had on Earth.
Yeah, perfect. So I know that this is the first launch for both of you. Why don't we take a look around really quick? So there it is on the launch pad, Falcon 9 and Dragon. Inside Dragon is your experiment. How are you guys feeling?
It is surreal. It is, it feels like a dream. And it's about to be a dream come true, not just for myself and Claire, but for our whole team, for students at Stanford who also have an experiment going up, and for all the students who assisted us in our citizen science.
Perfect. Guys, I cannot wait to see what you discover. Thank you so much for your time, and I hope you enjoyed the
See
launch.
that guy?
Thank you so much.
Engineer.
And we have another student experiment on board Dragon today. These guys are in college, but we have a high schooler here. You see Celine Coquelar. She won the annual Genes in Space research competition by designing a new method of detecting water contaminants. If successful, her work could be used to test water quality both in space and also remote parts of the Earth.
How old are you?
Genes in Space is made possible through Boeing, a startup called Mini PCR that makes equipment for biology research, and the ISS National Lab.
Okay.
All right, we're just under 6 minutes till, 6:56. I am having a hard time, guys, but we're close to terminal count. So let's bring back Shiva live from SpaceX headquarters in Hawthorne, California, and Daryl here on Florida Space Coast to walk us through the final moments of the countdown. Guys, take it away.
Megan's doing all right. She's doing good.
Thanks, Megan. Now, the SpaceX team is not working any significant issues with both Falcon or Dragon at the moment, and the weather.
Why do they want to launch my
continuing
genes
to trend
into
well.
space?
Like Daryl had mentioned earlier, we're keeping an eye on some clouds and intense precipitation, and we're going to keep our ear out to the loops to make sure we remain go for launch.
That was
the
the
range
ESA
does
flat
remain
gate.
go for launch at this time. Now, at this point, the Rocket Propellant 1 fuel
Squid's
is
got
completely
genes!
loaded on the
Squid's
second
got
stage
genes!
And nearly fully loaded on the first stage. Liquid oxygen loading is underway on both the stages. That'll complete at about T-minus 2 minutes to launch. At this point, we're also loading helium gas
They are
into
members
both
only,
the stages.
Fishy. Shame.
Falcon 9 uses that helium as a pressurant to backfill the propellant tanks as we consume that liquid oxygen and RP1 by the Merlin engines during ascent. Helium load began
That's
before
correct,
the
John.
broadcast went live.
Already
and
been
continued to
retracted,
top
though.
up until
Late load
about
was a couple
minute
hours
and a
ago.
half before the launch.
To make sure engine startup goes well, SpaceX performs an engine chill.
Bruh.
This happened,
Bruh.
has happened at T-minus 7 minutes. Flowed a small amount of the super chilled LOX into the Merlin engine's turbo pumps. And this is done to avoid a thermal shock to the system when that flow of super chilled liquid oxygen
Not a bad idea, Reflex,
hits the prop system.
I do have shirts.
Now Dragon
Merch,
began
EJ shirts.
its startup
Those are pretty cool.
sequence at T-minus 35 minutes when it coordinated timing with the Falcon 9. Dragon now currently undergoing vehicle health checks with the next big step just before liftoff. The
Max,
cargo
it is
spacecraft
big.
transitions
Yeah, big
to
place.
internal battery power.
5 minutes. New shirt.
Terminal count.
It's the same. It's the same shirt.
We just heard that call out for Dragon being in terminal
Did you
count.
fast forward? No, I haven't. Prepare to fast forward. Preparing to fast forward. Fast forwarding, sir. What am I looking at? When does this happen in the launch? Now. Chat, you're looking at now. Everything you see now is happening now. Then, oh, you missed it. Just now. Soon.
Discovery, go at throttle up.
And propulsion
Oh!
in preparation for liftoff just about 4 minutes away from now. We're also going to continue to hear call-outs throughout
Photo
that the engine
13
are
months.
sufficiently chilled in as we get closer to
No,
liftoff.
pass this
And on
part.
our
In fact, never
screen
play this
there,
part
you can
again.
see those clamp arms beginning to open
Oh.
around the second stage.
What are
in
those?
Between some of that cooling.
As the young kids say on the internet, what are those? Looks like we got some Starship stuff back there, especially this part. See that? That's Starship stuff. Just thought I'd let you know.
Discovery, go
Shoot!
at throttle up.
6 months. Instructions unclear. Hand in toaster. You missed it. Just now.
There you can start to see motion of the transporter erector away. It'll recline a bit before we step
It'll
further
move to
into
89 degrees off of
liftoff.
off ground level.
Coming up in just about a minute, Shiva. Checkouts of the second stage thrust vector control actuators. They are underway. This is often referred to as the engine wiggle test. This is when SpaceX moves the thrust nozzles slightly to make sure that the guidance hardware is go for flight.
SpaceX also likes to read books.
Again, that was a great
Thrust vector
view
control
of the
novels.
Transporter erector tilting back. SpaceX does the exact
agree,
same
but
checkouts of the first stage engines.
T-minus 3 minutes for
and that happens
CRS-25.
just seconds before ignition.
So, we got a couple of more steps here. They completed second stage TVC. Check out the wiggle test as Daryl was talking about there. The next thing that they're going to do, the next thing we should see is a chill down. See that little nozzle right there? So those fuel lines that I was telling you guys about to make sure that they fill up the second stage liquid oxygen and first stage liquid oxygen tank at the same time, the fuel lines are currently full of liquid oxygen because they're just finishing up topping right now. Once the second stage liquid oxygen tank is topped off, they will begin a gas closeout on the transporter erector. The TE is this white object right next to the rocket. It's that thing with the claw. The claw. Comes with the claw. I know, it's cringe. I get it. They will do a gas closeout, and what that gas closeout basically entails is pumping nitrogen gas up the fuel lines, and then they open up a valve at the top. They obviously close the valve off to the second stage.
Go at throttle up.
And then they open up that valve on the side, and the transporter erector will, as the kids say, rip a fat vape. Yeah, it should be happening in the next minute or so.
Discovery, go at throttle up.
T-Dave, 40-month resub. Glavic with a 57-month. Thank you very much. Do you think NASA will be back on the moon in 2 years? It's possible. We are fast-forwarded, fellas. Yep. The claw. See the claw?
1 minute, Dragon will transition
It
to
comes with the
internal
claw.
power. Falcon 9 computers will enter startup mode and begin final pre-launch checks, guiding the rocket through the last
Go for
seconds
launch.
before liftoff.
We might get a jellyfish here, Phil. Yep. Thank you for the bits and the subs, guys. I do appreciate it. Clocky with a 51. Probably not, John. I highly doubt it. 1.3s, eh? T-minus 60 seconds. Falcon 9 should tick into start.
Discovery, go at throttle up.
Should tick into startup.
Dragon is in countdown.
All right.
Both stages are now
Gas
pressurizing
closeout.
for
There it is.
launch.
Discovery, go at throttle up.
LG is go for Falcon 9, Sierra's 25 launch.
Launch director reports go for launch.
So range is
Worst.
go, weather is go.
2-month resub. T-minus 30 seconds.
T-minus 30 seconds.
I just said that. $20 seconds.
It's a beautiful time of day to watch this.
Should see the sound suppressors here on the left.
T-minus 15.
And here we go.
Pad deluge system should
10,
prime.
9, 8, 7, 6, 5, 4, 3, 2,
Desync count.
1.
Engine ignition.
Engine ignition.
And it looks like we got a liftoff. Liftoff, CRS 25.
SpaceX's Falcon 9 rocket launching Dragon on the 25th mission to resupply the International Space Station with cool science and a new advanced instrument to more effectively study our planet's climate.
Okay, stand by for the power and telemetry call after the pitch down range call. We didn't hear the pitch down range call, but they don't have the loop piped in. I'll bring it up on the back.
Power and telemetry nominal.
There we go. I cut in the mission control audio, guys. Stand by for the call for max Q.
Into flight, successful liftoff from the Kennedy Space Center.
1B.
Launch complex 39A.
That's not me.
For the point of highest stresses that the vehicle will experience during ascent.
Maximum dynamic pressure.
There's the call out for maximum dynamic
That's
pressure.
peak aerodynamic load on the vehicle. While the rocket is still relatively low down here, it's still moving through the atmosphere, so air can compress up against the front of the vehicle. When it compresses up against the front of the vehicle, it does compress the rocket. You don't want to accordion the rocket too much when you fly. That's no good.
Separation.
So
where
the call
first
for
and second stages will separate.
Second stage
the first
engine
stage
chill.
will flip around to make sure it's headed back towards the landing site, and our drone ship named a short call of gravitas.
They're out of the throttle
and then
bucket.
The second stage
Engine's
will
throttling
ignite
up.
its Merlin vacuum engine to boost Dragon into low Earth orbit during second engine start number 1. We just heard the call out there for engine chill-in on the second stage engine.
So engine chill means that they're running propellants into the second stage engine. They're basically priming the second stage for when they separate the rocket, they can fire up the engine right away. It also thermally conditions the engine because, once again, liquid oxygen, the propellants are really cold. You don't want to flash liquid oxygen into the engine and have it turn to gas really quick before it gets out the engine. That's probably not good for it. Okay, there's main engine cutoff.
Stage separation confirmed.
Got a good set. Stand by for upper stage ignition.
Fantastic sight.
Okay, start it.
First stage turning around, going back to the landing site there. Look at, you can see this first stage ignite. Oh, that's sick! What a shot! No, why'd you cut the camera? Come back!
On the second stage,
Ow!
as view toggles, you may catch the first stage. It is firing its Merlin 1D engines that burn on the first stage, lasting about 30 seconds. You can see the plume on the first stage on the left-hand side of your screen as we're doing.
So the first stage is doing its boost back burn here.
Stage 1 boost back shutdown.
Okay, boost back shutdown from the flight controllers confirmed.
Successful shutdown of the first stage Merlin engines for the boost back burn. Second stage engine.
No Super Dracos on the vehicle Reaper, but yeah, it could.
About the T+8 minutes.
No, it's a drone ship landing. Look at the trajectory, Nuke. It's a drone ship landing. This trajectory right here.
Welcome to our 25th commercial resupply mission to the International Space Station.
That's the first stage trajectory. The drone ship is right here. This other line that's getting further and further that way, that's the second stage trajectory.
Dragon flight to the International Space Station this year.
So if you look on the left here, you see some pulsing going on right there. You can see the shadow of Earth right there. There's the Terminator line. So that's where it's daytime and nighttime, right? The pulsing that you see on your screen is nitrogen attitude control thrusters. Built into the top of Falcon 9 is a bunch of compressed nitrogen tanks, and similar to how you'd blow the dust out of your keyboard, right? I mean, the keyboard dusters are CO2, not nitrogen, but they're using compressed nitrogen to be able to steer Falcon 9 and turn it around and get it ready to aim at the drone ship. They use those nitrogen thrusters to orient the vehicle. The other thing that you can see up there are the two waffle irons that are sticking off of the side of the vehicle. Those are grid fins. They're designed for control at hypersonic speeds. They're control surfaces. The reason they look like waffle irons is because when you're coming in at 5,000 miles an hour, a regular kind of control surface doesn't work very well. The waffle iron actually cuts the air in a really nice way that allows Falcon 9 to steer when it's flying back into the drone ship. Nice, Admiral. There you go. Why did they use nitrogen instead of CO2 in the rocket? Lighter. Nitrogen is less mass because it's just nitrogen and not carbon and 2 oxygen. Plus, nitrogen is inert. Rogue, I don't think I need to tell you why the other day, when SpaceX was testing Booster 7, why sometimes it might be good to test with inert gases and liquids, so it doesn't pop. Now, don't get me wrong. SpaceX during that test, they had to test with methane and oxygen because they were testing the starting system. Funny thing is, though, Rogue, that on Starship, SpaceX uses compressed nitrogen to spin the turbo pumps to start the engines. Interesting, huh? So first stage is coming back down. You can see some clouds there where the sun's going down, but my favorite part of the burn is about to happen. Okay, I was going to say my favorite part of this is about to happen here. This is where Falcon 9 is going to fire. The first stage is going to fire its engines, and if you look, the trajectory is changing a little bit. It's starting to slow down. And what Falcon 9 was doing there is not only slowing down, but they're using the rocket gases coming out of the engine to push the re-entry heating away. When stuff comes back from space, it starts to hit the atmosphere and it starts to compress the air so much that it rips the air molecules apart. And that releases a lot of energy in the form of plasma. Plasma kind of accumulates like condensation on the side of the vehicle, right? Not on the side, on the business end down there. SpaceX fires the first stage engine to push the plasma away. Supersonic retropropulsion. It's an idea that was pioneered by NASA for landing heavy payloads on Mars. SpaceX just used that to land first stages. Good idea, huh? So, first stage should be coming in. I am going to key the audio back on. So we should see some re-entry heating coming up here. Shortly. It's kind of hard to see it, but the first stage is definitely shaking around. It's coming back down to the atmosphere and starting to get into the denser parts of the air.
Speed on the left-hand side of your screen, that's the velocity of the first stage. We're going to see that come all the way down to 0. On the right-hand side of your screen.
And now the grid fins are doing their thing. They're steering it back to the drone ship. You should see it kind of land on my head here. I'm going to go over there so I don't get landed on. Coming through the clouds. Okay.
Stage 1 landing, leg deploy.
Leg deploy. Stand by. And stick it.
People really excited behind me. Right in the middle. 5th landing for this Falcon 9. 130th landing overall for an orbital class rocket. Beautiful sight.
Oh, that's nice. That's nice.
Next is second engine cutoff number 1, or SECO 1. We'll expect them to stop firing just about 30 seconds from now.
Very nice.
It's carrying
Discovery.
Here's the call for terminal guidance. Hey, Snow Crash, what's up, buddy? 8-month resub.
After we
passing. We've watched pretty much every single one of them.
We'll
Still
do a
good.
check to make sure that the burn performance.
And she was dead center.
We're in the
Stage 2
orbit.
flight termination is saved. Stand by after second stage engine
that
cutoff.
Called out as a nominal orbital insertion or a good orbit call out.
That's exactly what I was just about to say. All right, stand by for the call for nominal orbital insertion. Shiva literally took the words out of my mouth.
Discovery, go at throttle up.
Nice, 48. There you go. Mute hand, 63 months.
And back shutdown.
Okay, we have second stage engine shutdown 1, or SECO 1. Stand by for the call for nominal
orbital. So you
orbital.
heard a call out on the loops there for shutdown of the Merlin vacuum.
There it was. Shiva was talking over it. We have the call for NOI.
Nominal orbital insertion. So that means that the ground teams have assessed the orbit and stage 2 is right where we want it to be. And of course, that also means that Dragon is right where we want it to be, since it's been riding on the the second stage this whole time. Now, if you're just joining us, we're about T+9 minutes, 20 seconds into the mission. On to the screen next to me is a view of the Merlin vacuum engine with Earth behind it.
210 by 190. That's
now, the
a pretty good orbital insertion there.
Task remaining that is commanding separation of the Dragon spacecraft.
Yeah, I see it, Bandit.
From now. And we're hoping to have video
I saw it. I have the link open over there.
Of the second stage. We actually got a quick glimpse of it before. But we've got a camera that looks up into the trunk of Dragon and gives us a little peek at some of the cargo.
Yep, we're looking up the business end of Dragon here.
Section. You can see the EMIT payload there on the left-hand side of the screen. Now, the CRS-25 capsule will be joining
I know what you mean,
Crew 4 vehicle capsule Freedom, which is currently on orbit. So we'll be back to dual Dragons docked at the International Space Station.
Dueling Dragons?
CRS-25 will be headed to the forward Harmony port on
T-minus 1 minute 30 till deploy.
Expecting it to arrive on the 16th around 11:20 a.m. Eastern Time. There, it'll spend about 1 month attached at the International Space Station. Now, as for the cargo,
it's going to get there on Saturday morning.
Delivering more than 5,800 pounds of science, research, crew supplies, as well as vehicle hardware to the orbiting.
It landed
lab
on the drone ship, Airlicious.
And amazing, more views inside the trunk. Now, at this point, the second stage is performing its final checks to ensure that we're not imparting any unnecessary momentum or spin to the Dragon spacecraft. Once
no,
those
not really,
calculations are complete,
John. They've
Dragon,
gotten there faster. It's about 48 hours.
Stage will command separation, and shortly following separation, Dragon will conduct a series of health checks on its thrusters, its cabin, thermal, and solar systems, its navigation systems, in preparation for the upcoming 38-hour mission to the space station.
Okay, about 15 seconds. No, not 50. 30 seconds
30
until
seconds
deploy.
To go.
I just said that.
Joining us,
Shiva.
We're looking at the second
Seriously,
stage,
man.
Coming up real shortly to Dragon separation. This particular Dragon marking its
Jazz with 48 months.
flight.
Thanks, buddy.
And it also the third reuse of our upgraded cargo vehicle.
Nice, Brandon. There you go.
This view looking into the trunk of the Dragon capsule. That's our unpressurized portion of the vehicle.
Okay.
That's some of the payload that we're taking.
We're looking up the tail end of Dragon here. Ready?
Dragon separation confirmed.
Perfect.
Phenomenal. So with that,
very
CRS-25
nice.
Gently floating away from Falcon 9's second stage.
Very nice.
Again, coming up next, we've got some service section Draco checkouts, as well as nose cone opening. But that's actually going to complete my coverage here from Hawthorne. So I'm going to pass it over to Sandra at Houston to check in with the teams there. Sandra?
Sandra?
And thanks, Shiva. Welcome back into the International Space Station Flight Control Room. That was
I got you, Brendan.
beautiful.
Oh, cool. RCS checkout. Look. Oh, that's sick. Did you see that?
Confirmation of the nose cone deployment. And we did just get confirmation that the nose cone was successfully deployed. That nose cone does cover the docking hardware, the navigation and rendezvous sensor, and the forward.
Devlin, is it that quick? I don't.
The nose cone will stay open until the end of the mission, until after deorbit burn and just prior to re-entry.
RCS. The reaction control systems.
NASA and SpaceX's 25th commercial resupply mission launched from Pad 39A at the Kennedy Space Center
No computer
in Florida
state transition to
at
nose cone deploy.
7:44
I was going to say,
p.m.
that's not right. They haven't deployed the
8:44
nose cone yet.
Eastern
We'd
Time
see
this
it. You'd
evening.
see it open
It is
up.
currently in orbit and heading to the International Space Station. Dragon is filled with over 5,800 pounds of cargo and supplies, including a variety of science investigations, hardware, and fresh food for the crew on station, such as apples, oranges, cherry tomatoes, onions, carrot, garlic, tahini, and even shelf-stable cheese.
Cheese?
On board the International Space Station right now is the 7-person Expedition 67 crew, who I'm sure is looking forward to these fresh foods.
You're gonna...
The crew includes NASA astronaut Bob Hines,
I'll say that
European Space Agency astronaut Samantha Cristoforetti,
we have a loss of signal.
Roscosmos cosmonauts Denis Matveev,
oh, no, came
Oleg
back.
Artemyev, and Sergei Korsakov, as well as NASA astronauts Jessica Watkins and Kjell Lindgren.
Yikes. Lieutenant Dan, ice cream. All right, we don't have a loss of signal just yet. It should be coming up on a loss of signal through Newfoundland in a moment, but they should have a reacquisition of signal real quick through a handover through Goonhilly in Cornwall.
And we're just continuing to stand by on that nose cone deployment checkout.
Yeah, see? They haven't deployed the nose cone yet. But you're going to live on the ISS living off of a steady diet of government cheese and living in a pod down by the solar panels.
Dragon is slated to dock to the International Space Station on Saturday at approximately 10:20 a.m. Central Time. NASA astronauts Bob Hines and Jessica Watkins will be monitoring the approach.
Sometimes, Riv, if the mission calls for it. Yeah, see, there's no nose cone open yet. It should be happening here in a moment. The hook should retract and the nose cone should kind of open up like this. Just saw the launch from Miami. Nice, dude. I saw it in Pennsylvania and took a picture. You sent it soon. Nice, guys. Excellent.
On a computer ahead of Dragon's automated rendezvous and docking.
You got one, Stone? Hey, nice shot, dude.
And the two flight engineers were also joined by NASA astronaut Kjell Lindgren, who helped stage.
Okay, so check this out. They have a ground tracking station in Newfoundland over here. There's another one in New Hampshire, near me actually. And then the next ground station is actually, it's in Goonhilly. It's in southwest UK here. So it's right near where my finger is. My finger, look at my finger. It won't go up to the screen. I'm pointing at Point du Hoc, or no, Point du Hoc's over there. I'm pointing at Normandy. It's right there. It's at an old RAF base, if I'm remembering correctly. Goonhilly, Goonhilly. You yank. Yeah, Cerebral, because you guys have never pronounced like Mississippi, Alabama, or anything like that wrong, huh? Yeah, okay. All right. Yeah. What happens to the second stage? They will deorbit it. It will be disposed of, or fuck so. Actually, I'm showing the same picture twice. It'll be disposed of over when they get out over the South Pacific. The stage will turn around and do a burn. No one's going to see it, and it'll burn up in the atmosphere.
And we did hear that the first set of hooks is already driven, and the second set of hooks
I'm still coughing a lot,
is
Scruffy, but I'll be all right.
Nose cone deployment.
Okay. Yeah, Cerebral. Yeah, no, you got it. You got it, bud.
All hooks are now open.
Yep, Edwards. It's right there, right? It's at an old RAF base, right on the very edge. I forget which base it's called, but they have a tracking station there. And then there's another one in Dubai, and then there's another one in the Maldives. Maldives. I like saying Maldives, but I know it's Maldives. I get it. It looks like this Dragon is not using Starlink. They're still using the ground tracking stations. Maldives. Sorry, I'll stop.
Everything continuing to go smoothly. We should have confirmation here just shortly that the nose cone is successfully deployed.
We should be getting an acquisition of signal through Goonhilly here in a moment. Fellas, if you're in the UK, like in the Midlands right here, or in Wales, or at the southern part of Ireland right here, the stage and Dragon might be high enough that they're in the sunlight. The Terminator line is there. What the heck? Oh, nose cone opening. There we go. You guys actually might be able to see it. It'll look like an airplane flying across the sky because the sun's reflecting off of it, but it'll have no strobe lights. It'll just be... It'll look like an airplane. Passing you a touch too far north. There's the nose cone opening up right there. We got a great shot of that. It's night. Yeah, I know, Skippy. I know it's night where you guys are. I understand that because world and stuff. I get it. But Dragon might be high enough that it might be in the sunlight.
Here shortly.
So you might be able to see it. I'm telling you, if there's no clouds, she's coming over the southern coast of Ireland right now. I mean, because look, when they open the nose cone, we'll see if there's sunlight. This thing should be in the sun. Oh, that's so cool. Nose cone opening shot, man. Oh, yeah. You can see the RCS firing out there.
And again, this nose cone does cover the docking hardware as well as the navigation and rendezvous sensors and the 4 forward bulkhead Dracos.
Yeah, dude, it's definitely in the sunlight. It should be close enough. So it's right over the southern tip of Ireland right now. Right over the southern tip of Ireland. Gonna pick up some spuds on the way. Send them up into space. You see it, Skip? Like I said, it'll look like an airplane. But no strobe lights, no blinking lights. It'll look like a plane. You should be able to see. See, it's in the sunlight, dude. You can see it over there. Should be able to see this thing. This is a resupply mission. Yep. So she's almost over Cornwall right now. Like, it's gonna fly directly over Cornwall. There's a shot of Dragon from the second stage. You can see that the nose cone, in fact, was open.
And we're continuing to stand by for nose cone deployment.
It was fine, weather guy. Yep, there were anvil clouds forming over Sanford, but the wind was blowing southwest to northeast, 18 knots. Everything was good. No lightning violations, no nothing. It was nice and clear all the way up. Nose cone deploy is complete.
With Dragon now safely on its way to the International Space Station and the nose cone successfully deployed, that will do it for us here in Mission Control Houston. Thanks so much for joining tonight, but I hope you'll tune in for the docking coverage on Saturday, beginning at 9 a.m. Central, 10 a.m. Eastern Time. But for now, I'll send it back over to the Kennedy.
Looks like I gotta get up on Saturday morning. Marta, you sent me a thing?
Thanks so much for walking us through that. That's going to wrap up our launch coverage of NASA's and SpaceX's 25th Commercial Resupply Services mission. As Sandra said, Dragon is on its way to dock to the International Space Station and is set to dock on Saturday at 11:20 a.m. Eastern Time. We will have live coverage of that beginning at 10 a.m. And if you're interested in tracking EMIT, again, one of those experiments on the mission that's studying the Earth's climate, you can do that by scanning this QR code you see on the bottom of your screen, or just write down the website here. It's earth.jpl.nasa.gov/EMIT. Once attached to the space station, EMIT will start collecting its first measurements by the end of this month. Again, thanks for joining us. We leave you with a replay of tonight's
She's over the Netherlands right now.
Enjoy the rest of your evening.
Oh, I will.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Engine ignition.
It's basically over Alsace right now.
Liftoff of SpaceX's Falcon 9 rocket, launching Dragon on the 25th mission to resupply the International Space Station with cool science and a new advanced instrument to more effectively study our planet's climate.
Cool science! Yeah, science! Now it looks like she's making her way south over Bavaria right now. Should be moving into Austria here, and it's gonna make a track basically right over. It looks like it's going over Slovenia as well. Here, I'll bring the track up on the main screen. Main screen, turn on. Yeah, so Austria right now. Cool science has mega moon rocket vibe. Yeah, I know it does. Weird science. Oh. Too cloudy anyway, maybe next time. Yep, over Austria in the Alps right now. Oh, also fellas, here, I got something you probably want to see. This is a shot from
and there you go.
Our buddies over at NASA Spaceflight. There's main engine cut off. Or we should be getting our main engine. Yeah. Okay. Okay. That's nice. Yeah. Yeah, this is coming from our buddies over at NSF. That's the second stage over there. The first stage is boost. You could see the first stage boosting back. This is what I mean. Over in Europe, the sun's about to come up. Well, it's actually going to be another hour, so another couple hours till the sun comes up. But over here, the sun is just going down. So the sun, where the rocket is up there, the plume is illuminated by the sun, but it's dark down on the surface. You guys have the reverse of that over there, so you should be able to see it. There's the first stage. Look at it. They got the first stage outgassing. Did they get it all the way to landing? Hold on. "3 a.m. and I can already see it brightening in the northeast." Ando, it's 9 o'clock over here, and there's still a shed of sunlight out there. Just a little bit. It's like the opposite of what you got right now. NSF, more like NSFW. Am I right? Mutter, that was fantastic. Very good. Right now, stage looks to be over the Balkans right now. Serbia, if I'm looking at that right. Did I miss the landing? Yep, just happened. Well, actually it was a little while ago. Pop, and then it flew over you guys. And you're near the Terminator, so a couple of people over Europe said they saw it. Crappy pig, but not bad considering how far you are away. Nice, Brian. There you go. Nice, nice. So we'll track this a little bit more, and then I think we're good. I mean, fellas, that landing was spot on. Let me go back over here and ow, NASA, Jesus, man, why you gotta be like that? So there was some things that we could check out here. Finally got around to watching For All Mankind and loving it. Have you seen much of it? I watched the first season. I don't care about the second or third season. So you can see a bit of Starship's pad over there, fellas. I noticed this shot right here, and then it looks like they're working on some prop tanks right there. Repellent tanks, from what I can tell. There's another crane here doing something. I don't know. But the orbital launch pad is there, and it's just chilling. Phase burn in 22 minutes. Got it. So, launch was great. I'll get you guys to the landing here. I mean, the landing is the freaking best part, dude. Watch this. Here. This was the landing from that booster. 5th flight for this booster. Dude, through the clouds. That's sick. Punching right through the cloud. Landing leg deploy. Camera got a little washed out, but we did pretty much get uninterrupted footage all the way down. Oh, that's so legit, dude. Looks like they had a little bit of residual fire coming from the bottom. Fellas, that actually does happen, because turning off the taps on a rocket engine is like if you shut off a garden hose, right? The valves are upstream from where the rocket engine is, right? And so when they turn off the valves, you do get some residual, just like if you shut a garden hose off, there's some water left in the line. That residual fire that you see that's going on down there, that happens. This stuff right here, that happens. That's just extra propellant getting burned off that got stuck in the engine when they shut it off. After all that gets evac'd, what they do is they purge down the engines. You can see there's a lot of venting and stuff going on right here. This is steam, though. All this stuff that you see in the foreground, that is steam, because what they do is if we... Discovery, go at throttle up, username, 26 months. So, if you look right here, the drone ship is splashed with water. They actually film cool the deck of the drone ship. They spray it down with water, so when the rocket does come and land, instead of melting the metal on the drone ship, it just heats up the water and turns it to steam. Watch, you'll see the water, you'll see it start to dry out right here, right around the X. Watch, even before the rocket gets near the ground. See? It's gonna get evapped off real quick. And the lens flare kind of made it not useful. Not a useful shot, but there you go. All the steam right there. And look at the deck of the drone ship right after landing. It's dry. It was wet a second ago. That's how much energy gets put out from those things. It's enough to freaking basically turn all that water into steam instantly. Down, down. Yep, little bit of residual there. After most of the propellants inside of the engine burn off, what they do is they hit the engines with helium. They start pumping gaseous helium through the engines to evac all the liquid oxygen out. You want a lot of these propellants to burn off, and you also want all of the oxygen out of the engine as much as possible. The reason is because, well, oxygen oxidizes things. It rusts stuff from the inside out, and it rusts metal very good. And the rocket engines are made out of metal very well, very good. So what they need to do is they start pushing gas through the engines to get all of the liquid oxygen out of there so it doesn't rust the engine from the inside out. You think salt will rust your car really quick? Pour locks on it. There'll be no car left. Everybody's in the salt belt. It's like everybody lives in the salt belt is like, yeah, I doubt that. No, seriously, LOX is super corrosive. If you watch here even more, if we get the second stage engine cut off, they'll shut the engine off and you'll see the purge lines. You'll see the purge lines on the second stage do the exact same thing. They pump helium into the engine to get all the liquid oxygen out, because even like a 5-10 minute coast for the second stage with liquid oxygen in there, it's enough to rust it, to break things. So watch, they'll shut the engine off and you'll see a puff of gas come out. See? And then the purge lines will turn on and they'll hit helium into the engine to see, there it is, to get all the liquid oxygen out of there. Pretty cool, huh? Little thing on propulsion there. The ISS did a passover just after launch. WD-40 got a view of the launch on stream, and DAS showed it on the NSF feed. Cool. There was a green glow near the base just before launch. Is that normal? Yep. Yes, that is totally normal. What you're looking at is the starter motor. So, Dead Scum, you ever grill before? Blinga's right. That's the right response. You ever grill something before? You ever throw some lighter fluid on the grill and then throw a match on it? Basically that. Falcon 9 uses what's called pyrophoric ignition. So what is that? Pyrophoric ignition. Okay. Pyrophoric. So it blows up when it hits water? Yeah, that's right. They use two compounds called triethyl aluminum and triethyl borane, or TTAB for short. TTAB are inside of the turbine in little cartridges, like little CO2 cartridges. And I don't know the exact design for the Merlin engine, but I'm pretty sure they use a perpendicular radial TTAB ignition system. So basically, this one has TB, this one is TEA, right? And the two injectors, they shoot at each other to get the TEA and the TEB to get the TTAB to mix. And when it mixes, it becomes pyrophoric. So what does that mean? When it finds oxygen, it explodes. When it finds oxygen, it's gonna blow up. And there's oxygen already in the engine from where they trickled the propellants in. So the TTAB ignition is a nice green flash. You get a nice green flame. And then immediately it turns yellow from where the kerosene starts burning. What the TTAB is designed to do is designed to get the turbo pumps. It's that huge explosion, and I said it happens in the turbine. It's a huge explosion to get the turbine spun up fast enough to start pumping fuel into the engine. That's all. Rocket engines have jet engines attached to the side. Usually they have a jet engine strapped to the side, but instead of the jet engine making thrust, it has a fuel pump attached to the front. instead of a turbine, and a compressor instead of a compressor, it has a fuel pump. Hence, turbo pump. You have a turbine on one end, and you have a fluid impeller on the other. Turbo pump. Engineers, they're very literal when they name things. It's pretty straightforward stuff. So they shoot the T-tab into the turbine. The T-tab blows up because the turbine uses some of the rocket's fuel and oxidizer to keep the turbine spinning, so it keeps the fuel pump spinning. They spray the T-tab in there. It finds the liquid oxygen in there, and it blows up, and that ignition activates basically the combustor in the turbine. Turbine spins up, starts pumping fuel into the engine, and there you go. What that all looks like is this. See the green flash? There it is. And then all the engines get up and running real quick. It turns out when you have a lot of thermal expansion and you have a high airspeed over a turbine blade, the turbine starts spinning really fast. So Merlin engines here are an open cycle engine. They're an open cycle rocket engine, meaning the turbine exhaust just shoots out the side. That's part of the reason why when Falcon 9 lands, it's covered in soot. When Falcon 9 comes in for a landing, you see this thing will come down, it's all covered in black soot. Now, two things. That is not from the rocket engines. The rocket engines are burning off a lot, most of the carbon that gets, most of the RP1 that gets pumped in there. Most of this soot happens from the turbine outlet. So if we look at a Merlin 1D, right? You look at this is a test from SpaceX. This is the Merlin 1D firing. If you look at this thing, when it goes, they'll show a close-up view. You have your engine right here, and your engine is making the explodey stuff. That's this down here. But the turbine, see how sooty the turbine is running? Hey, I know that place, Devlin. You see how much soot? If correct, EJ, that's what's caused the Falcon Heavy core to miss the barge. Yeah, the T-tab didn't ignite, Barry. Yeah, didn't get the engines running, so the grid fins steered it away from the barge so they don't accidentally sink their battleship. Yeah. You sunk my battleship. Falcon 9 is a really good guided weapon, only it's not designed to crash into things. It's designed to stop at the last second. But other than that, it's pretty much the same thing. I mean, bombs use grid fins, dude. Bombs have been using grid fins for 50 years. True story. So, if you look at the turbine over here, the turbine is shooting soot out. Anybody here drive a truck? Anybody here drive a diesel? Drive a diesel truck? What happens when you get black smoke coming out the exhaust with a diesel? It's rolling coal. I'm serious. That's exactly what's going on. Falcon 9 rolls coal like you would not believe, but they don't do it to be obnoxious. Two things. They're running extremely fuel rich here, and you get a lot of soot coming out to make the most amount of power. That way, if you spray a lot of fuel into that turbine, the turbine's right here, you spray a lot of fuel and about half of the amount of liquid oxidizer in there, all of the oxygen is going to combine with all of the fuel, and all of the fuel that did combine with liquid oxygen is going to combust. That does leave excess fuel byproduct. The turbine is running very, very fuel rich. So fuel rich means that the amount of fuel that they're putting in is not equal in any way, shape, or form to the amount of oxygen they're putting in there. The end result is rolling coal. Falcon 9 uses RP1. RP1 is a very, very highly refined version of kerosene, which in the petro kind of hierarchy of things is pretty close to jet fuel or diesel fuel. It's very similar. It's a distant relative. So Falcon 9 does roll coal. It absolutely rolls coal. But they do that. The reason why it runs fuel rich is so they get a very, very complete combustion and they make the most amount of power. Because anybody that knows with a diesel truck, you see black smoke coming out, that means you're running fuel rich and you're making the most power you possibly can. That's why those guys with diesel trucks drive around and they shoot soot everywhere, because they're making more power that way. You can make your engine go brrr harder. That's the reason. Now, The other reason that they're running fuel rich is for temperature purposes. You guys ever wonder why some rocket engines could fire? And like, okay, spoiler alert, right in this area right here, it's extremely freaking hot. Right here. Not here or here so much. Not here, but right here. It's pretty damn warm. How does it do that without melting the metal? Well, rocket engines do not run anywhere near stoichiometric. They run extremely fuel rich to prevent the metal from melting. Or, if they're using a fully cryogenic propellant like liquid hydrogen or liquid methane, a lot of rocket engines run the liquid fuel through the nozzle first on the outside through a cooling channel to cool the nozzle and heat up the propellant so they burn better. Diesel, RP1, Jet A, it's all, yeah, they're all brothers. So, the soot that you see from Falcon 9 actually landing here is from the turbines. That's from the turbines. It's the turbine exhaust is getting pushed up out the side, and it sticks to things. Like I said, anybody that's ever worked on a diesel knows about the carbon soot. The carbon soot gets everywhere. Smoke tubes in diesel like that are lots of safe power, but not efficient and damaging in the long term. I mean, yeah, if your engine's going to make more power, Kev, yeah, it's going to break it over time. They do make more power, and diesel engines, when they run fuel rich, do stay cooler, but still, yeah, it's probably not good for it. The rocket engine has to do that. That's the reason. It has to do that. Yeah. Literally would take a generator at old place I worked at, and instead of filling it with diesel, I would use Jet A with additives. Nice, nice. Is that like an afterburner on a jet? Chuck, no, not really. What a jet engine does is it has a compressor at the front, right? What's called an axial compressor. So it's sucking in air, and then that from the compressor it goes into a funnel, and then it pressurizes that air, because the same amount of air flowing in going into a smaller area is going to pressurize the air, right? And where that air pressurizes, from there it goes into what's called a combustor. And the combustor, when the air goes into the combustor, you have basically a plenum inside of the jet engine. And that plenum, which is basically just an area to store air, right? Like, that's basically what it is. It goes into a combustor and it depressurizes when it goes into the combustor. And right when that fuel depressurizes in the combustor, or when the air depressurizes in the combustor, they spray fuel in it. They spray fuel into it and light it on fire. The resulting thermal expansion, right out the back of the jet engine, turns the turbine, which turns the compressor back up at the front of the engine. Now, what does an afterburner do? Well, jet engines do have some leftover fuel and oxidizer coming out of the back. They have some leftover unburnt oxygen coming out of the back of the jet engine sometimes, coming out of the turbine blades, and it's already staged. It's already nice and hot. If you get the gases nice and hot, they burn really, really nicely. So that gas that comes out of the turbine, what an afterburner does is after the combustor, the burner, they spray more fuel into the exhaust, and any oxygen that was not used during the combustor process gets blown up and shot out the back. That's what the afterburner does. That's what that implies. After the main burn, after the combustor. That's what an afterburner does. Now, no rocket engine does stuff like that. But there are rocket engines that do something similar to that. It's similar. It's not exact, but it's similar. Hey, KevHawk, 18-month resub. Does Dragon have enough power for once around if they have a power supply issue on launch? Yes. I don't know how electrical power is conducive to deorbiting and landing, Goalie, because Dragon can come in ballistic if it needs to. But yeah, it should be fine. KevHawk, the company I work for spends time fixing the smoke-tuned diesels for diesels. They're a blight on the diesel industry as a whole. It's a shame, yeah, because, yeah, Kev, you're not running very efficiently, right? Yeah, and it really likes to break things. But, anyway, so, Chuck, there are rocket engines that you could say afterburner on, but it's not called an afterburner, Okay? So something like Raptor. You guys know Raptor, the Starship motor. So the motors that are on Starship, these... MVAC startup.
Discovery, go at throttle.
Oh, that was the second stage deorbit on the mission control audio. Stage deorbit is complete. Nominal deorbit burn called from the mission there. I still had the audio up. Cool. So let me get you a picture of Raptor engines. So these things right here. See those guys? I mean, those are Raptor 1s. Those are old at this point. Raptor engines don't have an afterburner, Chuck. They have a preburner. Yeah, it's called a preburner. What does a preburner do? Hey, Fruity213 sub. Thank you very much. What does a preburner do? Well, think about it like this. Raptor uses methane and liquid oxygen. Liquid methane, liquid oxygen. There are 2 turbines that pump liquid oxygen and liquid methane into the Raptor, right? But the fluid impellers for liquid methane and liquid oxygen on a Raptor don't just pump fuel directly into the combustion chamber. They do what's called a staged combustion cycle. Raptor particularly is using what's called a full flow stage combustion cycle. What does this mean? Well, Chuck, think about this for a second. You have your pump, you have your fluid impeller, and that impeller is attached on an axle, and that axle is attached to a jet engine. A turbine, very similar. A turbine, very similar to, a jet engine, right? But here's what they do.
Go at throttle up.
Instead of in the turbine, you're spraying fuel and oxidizer and then dumping it overboard, right? Like what Merlin does. Raptor takes that soot thing that comes out the side of the turbine, right? It takes this, and that goes into the engine. This fuel-rich mixture goes into the motor instead of being dumped overboard. And it's not going into the side. It's not going into the throat. It's going into the combustion chamber. Now, there's 2 of these pre-burners on Raptor. There's one for the oxygen side of things, and there's one for the fuel side of things, for the methane side of things. The methane one runs fuel-rich, just like what I'm talking about. The oxidizer one runs oxidizer-rich. So you have these pre-burners are literally jet engines, and they're shooting out a jet engine exhaust. Those 2 exhausts from the pre-burners go into Raptor's main combustion chamber. So you have a very fuel-rich mixture going in from one side, and then you have a really oxygen-rich mixture going in from the other side. And then they combine, and then that goes into the combustion chamber, and they spray a little bit more LOX in there, and then blow it up. So Raptor is kind of an afterburner engine, but they're not afterburners. They're pre-burners. It's like having 2 jet engines shoot into a rocket engine. And the rocket engine is your afterburner. But since the rocket engine is your main source of combustion, they're pre-burners instead of afterburners. Pretty cool, huh? Does Von Braun's research and technology still play a big role in Raptor engines? No, not really. Not really, Stroker. The Raptor engines are on another level, dude. Yeah. If Von Braun's original research is a little calculator that can do basic addition, subtraction, stuff like that, Raptor engine is a graphing calculator. It's one of these. This is like the 5th time I'm listening to this explanation, and each time I learn something new. Either I have a bad memory, as EJ is good at finding new things to explain. Devious, I never explain something the same way twice, ever. Ever. I do that on purpose. I always explain it differently, a little bit different every time, for that exact reason, so people don't get bored of me. Yeah. I always try to find a little bit of a different way to explain it. And once again, that does 2 things. One, that demonstrates I know what I'm talking about and I'm not just regurgitating a script, which is true. I literally read about this stuff in my spare time because I'm a loser. Go figure. This is This book is on my desk. Modern Engineering for Design of Liquid Propellant Rocket Engines. This is where I learn all this stuff, from books like this, and rocket propulsive elements. But, yeah, I always try to explain things a little differently every time. Keeps things fresh. Hey, Riveran, 1 year streak. That's a 12-month resub. But yeah, Stroker, Von Braun's research in propulsion wasn't... See, that's the thing about Von Braun, okay? If you really want to learn technical things, Von Braun never ran NASA. He was the director, he was a chief engineer, okay? He's the director of engineering. He's a project manager. That's what made Von Braun's rockets so good. Because Von Braun was really, really, really good at seeing the macro picture. And this is not something that I read in a book either. I've talked to guys that worked with him. And I have those interviews on stream somewhere around. When I went to Space Fest in 2019, I talked to a bunch of people that worked with Von Braun, a bunch of engineers that worked with him. Every single one of them said the same thing. They said that he was one of the most notorious project managers around. He knew every single facet of the rocket from top to bottom, even if he didn't engineer it. He knew every single part of the Saturn V. He could point at every single bit and tell you what every single piece does. Does that remind you of anybody? There you go, Victory. That's right. Thank you for explaining it to me. You're not a loser. You're just passionate. I love this stuff, man. Rockets are awesome, dude. Also, explaining it differently might get different people to understand. Sorden, I've gotten pretty good at this teaching thing over the last decade. Das is a good project manager. Yeah, he is. No, Elon. Elon knows every facet of Raptor from top to bottom. If you watch Tim Dodd's videos where he interviews him, he knows what every single piece does. Elon does the same thing. And Elon is not the CEO of SpaceX. That's Gwen Shotwell. Elon's the chief engineer. And he's a very good project manager. He's like Von Braun in that regard. That's what made Werner von Braun so good. He can manage projects. And he can manage it on a timely schedule and get stuff done. Yeah, short line, I guess. He's technically the president of the company. Yeah, there you go. So, you know, it's a good question. You know, is any of Von Braun's work still floating around? If anything, it's the systems engineering. That's the next book that I have on my desk. Systems engineering. Von Braun basically wrote the book on systems engineering for space programs, and that still does get used from time to time. Yeah, Soapbox, I got it backwards. Thank you. Gwen Shotwell's the CEO and president. Elon's the chief engineer and CEO. That's right. Point is that Elon doesn't really run day-to-day operations for SpaceX. That's what Gwen does. Elon's the engineer. He oversees Starship development. And Falcon 9. Falcon 9 is his design. But he doesn't engineer every single piece of the rocket from the ground up. He has engineers to do that for him. He's the guy that puts the whole thing together, that makes the whole project come together. Do you think Elon still watches rocket launches? Every single one of them, Stroker. I guarantee that. Every single one of them. Gwen is actually really cool. I talked with her a few times. She seems cool as frick, Devlin. You know why I like Gwen? Because Gwen... It's not about anything else. It's just about the rockets. You can tell that lady is obsessed with rockets. Like, probably more than me. Like, way more than me. Like, I look like a filthy casual compared to that woman. Like, that's why I like Gwen. Because no bull crap. No bull crap. She seems like a really cool person. She doesn't take no crap from nobody. I like that. That's cool. Hey, Yarg. Do I know the Muffin Man? Nah. Wait, was that the guy that lived on that road or something? I don't know. I don't remember. Gwen is an amazing personality for work management at a company. Cool. But yeah, Stroker, that's actually a really good question. Yeah, Von Braun was a good project manager. He could oversee stuff. And once again, I have this right from a primary source. I remember someone asking her where SpaceX will be in 100 years, and she said interplanetary. Yeah, that was her TED Talk short line. I remember that. And the guy was like, yeah, I very much doubt that. And she's like, are you serious right now, guy? You asked the damn question. Do you know the Pudding Man? I do know the Pudding Man, yes. Hans Koningsman was sort of the Von Braun for SpaceX. Yeah. So Hans was the director of launch operations for SpaceX for like 20 years. He retired recently, but yeah. Director of launch operations is a little bit different. Tom Mueller, that's what I was getting to, Devlin. Like, Elon didn't design the Merlin engine. A guy named Tom Mueller designed the Merlin engine. Tom Mueller is a rocket propulsion scientist that worked for a company called TRW for a long time. TRW is and Tom Mueller didn't work for them when they did this, but TRW built the LMDE, the Lunar Module Descent Engine. Yeah, he's like, you guys want like, if we had like baseball cards or trading cards for like rocket scientists and chief engineers, Tom Mueller would be a very, very collectible card. That guy's like the Babe Ruth of rocket scientists. Seriously. Designed Falcon 9's engines. Pretty damn good. Holographic rare. Yeah, exactly. Well, I just talked with you guys, it wouldn't be baseball cards. Because one, half of you are from overseas and you don't know what the hell baseball is. Two, the other half that lives here probably doesn't care. There might be some baseball fans out there, and if that's good. Think anyone's ever going to catch the Yankees? Probably not. Hopefully, there's the wild card, am I right? But Pokemon cards would probably be better for you guys. Am I right? Hey, you can be like, well, EJ, what do you... Yeah, you know I'm right. Be quiet. Tom Mueller is, yeah, like a holographic Charizard or something, dude. Yeah, absolutely. Yeah, that's a good one, Hired. Go Brewers. There you go. Detroit Tigers. You got a Tigers fan in here. Nice, man. Baseball. Cricket is the way. Cricket's cool. I don't mind cricket. But I grew up with baseball. I didn't grow up with cricket, so I like baseball better. Mets winning it this year. That's a fact. Write it down. Brian, on the one hand, frick you, New York team. But on the other hand, you also hate the Yankees as much as I do, being a Red Sox fan. So, best of luck to you. Shut up, but best of luck to you. Baseball? What's that, Wookie? Oh, God, no, not Pesepalo. Pesepalo is different. Boo this man! You got to know what a crumpet is to understand cricket. Yeah, that's fair. Let's go Blues. Wrong sport, man! Wrong sport! How dare you? How dare you? Yeah, I voted for the Red Sox All-Stars. We are united in our hate for the Yankees. Screw them. Boo Mets and Yankees? New York teams. But yeah. This is fun, guys. I like coming back in and talking about this stuff. It's pretty cool. Rocket engines are sweet. They're pretty freaking rad. So check this out, guys. We're just coming up to the end of the cast. Stage 2 is re-entering over the South Pacific right here. The Stage 2 did a deorbit burn over Diego Garcia, and look, stand by for the call for loss of signal. I'll never apologize. Let's go, Cards. Go back to Missouri. Get the frick out of here. Freaking Midwest teams. Stage 2 is about to have a Viking funeral here. Will they ever show the onboard cam? Nah, there's no ground tracking station out there hired. They do have one in Tasmania, but this is not, it's not close enough. It's a sad thing, but Stage 2 actually says goodbye to MCCX? Oh no. Oh no. Now I feel bad. Go back to Utah. I'm not from Utah. That's the Southern Ocean, not the South Pacific. Who cares? There's nothing down there. It's the last computer state called goodbye. That's really sad, actually. They aren't streaming it, they just have the track. Stage 2 is RIP. How dare you? I'm down there. Well, you're not down here, you're down there. Down here and down there are two different things. Unless you're over here, in which case you're way down there. When will it disappear? Well, so you're not down here. You're not down there. You're over there. Differences. Shuts, there's a difference. You're over there, not down there, not down here, but over there. When will then be now? Soon. Yeah, so, okay, if you're wondering why the stage is still going, they don't have acquisition of signal right here. The stage deorbited when they didn't have communications. But who's on third? What, we're talking about baseball again? Did you just assume my down under? Oh, God. No? Failed launch? Oh, no, Jovian. The second stage deorbit. Dragon insertion was completed over here, and then they did the deorbit over Diego Garcia, and yep. Okay. Yeah, see the camera tweaked for a second? Yeah, that's gone. That's gone. Devlin, that's really sad. The network continues to propagate the orbit despite it going into the Earth. It's like time warping in Kerbal. It doesn't understand that it's gone. Shouty is gone.
Discovery, go at throttle.
Agent Smart, 19 months. Oh yeah, see the camera skip around? I was gonna say, oh, they have a reacquisition of signal, but it's basically just gonna keep going and just keep repeating. See? It's just gonna keep going back and repeating, of course. Well, as stage 2 burns into a fiery plasma grave, watery plasma fire grave, it's gone. I think that's gonna do it for me, guys. AOS, my boat? Yeah, maybe. The network is sad to find out it's gone. And on that bombshell, we're good. Stage 2 landing, burn starship. Yeah. So, that was CRS 25 coverage. I hope you guys enjoyed it. It was fun. Really, 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 really enjoyed doing these launch things. If you like it, hit the follow button. If you think I'm weird, yeah, you're probably right. You don't need to hit the follow button if you don't want to. You do, though. No, not you. Not you. Not you. You. Yeah. You thought this was cool, right? Right? No, where are you going? No, come back. Please. Chat, he's gone. It's only in one piece for a few seconds after hitting entry interface. Yep. I followed because you're weird. Okay, cool. All right. And if you stayed, right on. I'll be back tomorrow at noontime. Here, let's see if we can drop the raid on. Raid? He said raid on. Let's see. Who's popping around? Raid on? Where? Dude, there's nobody around tonight. My buddy Grav Shark is playing from some Tarkov. Let's see if we can boost Grav up. Grav is a space nerd too. He just plays a lot of Tarkov. You can make fun of him for having a mullet. You can do that. It's doable. Go tell him I said that it was okay.
Discovery,
tell him I said it was okay. Guys, it's been a good solid 10 hours of streaming. I'll see you guys tomorrow, noontime again. I think we're going to keep going with Kerbal. We got Kerbal and we got Racing, I think, tomorrow. We'll see. See what we got. Are we doing Flight Sim tomorrow? I do want to play more KSP. I want to get this MLV stuff done. I want to see if the crane thing works, Lumprod. I'm actually super curious about that. So, we're going to play more Kerbal tomorrow. If you're still here, first of all, I just can't believe you're still here listening to me rant for long periods of time. The next launch that we got on the books is Firefly Alpha on the 17th. That's on Sunday. I might be around for that. I don't know. Anyway, have a good night, guys. Go see what Grav Shark's up to. I'm going to shoot him a raid here in a moment. And like I said, go over there, at least say hi to him. At least say hi. He'll be pumped. He'll be like, "Whoa, EJ, oh my god." And tell him to stay frosty while you're at it. Trust me. He'll be like, "What? Trust me, it'll be funny. It'll be dude, look, would I steer you wrong?
Discovery, go at throttle up.
Much? Let's go raid Grab Shark, guys. I'll talk to you tomorrow. Thank you very much for watching, and have a good night, okay? I'll see you later. I wouldn't steer you wrong. Jeez. No, I wouldn't. Maybe a little. All right. See you guys. I'll see you tomorrow. I will steer my fist into your face higher. Jeez. You hang up first, chat. You hang up first.